Okay. Yeah, why don't we get started and more people will file in. Okay, so this is lecture 8 and we'll talk about constraint programming, and I'll introduce that a little bit more once we get into it. But as always, we'll do some important logistics and introduction stuff. So there's a lot of logistics to talk about, so do be aware of all of these due dates. So first and most importantly, the final project partners. That assignment is due tonight at 11:59. I'm pretty sure everyone's already submitted it, so don't need to worry about that. The next step of the final project is the proposal, which is due this coming Monday, 10/28. Again, the details of what the final project proposal entails is on the website, and there's a big document that explains a lot of stuff. Try to follow that. Again, whatever you propose is not necessarily binding. We'll be giving feedback on your proposals, and you'll have if you want to switch things around, that's completely okay. Just keep us in the loop. But the point is for you to start thinking about projects now. Importantly, I don't remember if I mentioned this last class, but late days are not allowed on the final project, so everything must be submitted on time. Otherwise, there will be big penalties that you don't want to worry about. Homework 3 is due on Monday, this coming Monday, and homework 4, which is the last homework, that'll be released this weekend, ideally. It'll be due in 2 weeks, so most likely on November 11th. And one thing I want you to keep in mind is that there's another checkpoint for the project checkpoint, which is on November 21st. So it's kind of your responsibility to balance how you're working on things. As far as homework 4 goes, there's 2 parts to it. The first part, you can probably complete it after today's lecture. The second part, you might have to wait until next week. So what I might suggest you do is just, once homework 4 is released, maybe do part 1 as soon as you can, get it out of the way. Then you can dedicate some time to working on the project. And then next week, when we have lecture, you can just finish up part 2, and there won't be that much to worry about. And then spend the remaining time on the project. Are there any questions regarding homeworks or the project?
There's only 4, right?
Yeah, homework 4 is the last one, yeah. Questions about the project? Okay, so before we get into stuff, last week we had the guest lecture. So ideally, I just want to hear a little bit from each one of you, since there aren't too many of you. Just tell me something that you learned from last week, something you found interesting, or anything you still have questions about. Just any tidbit that you want to share. So I'm going to ask everyone to share. I know it was a long 1 week since we've had that lecture, but try to see if anything stood out. Yeah, super niche, but I guess it is a problem that has to be solved. So cool. Yeah, I hope you guys enjoyed the lecture because I found a lot of things really fascinating from that. Good. Maybe that inspired you for your final project. Maybe not, but just good to understand. Okay, what even is this slide? What's the warm-up? Ah, yes, I remember. Okay. This is going to seem like a really strange question, but can one or some of you just tell me what is Uber? Pretend I know nothing about it, which is kind of funny because I took an Uber to come to campus today. But let's just pretend I don't know anything about what Uber is. Just explain it to me.
Uber is a technology company which has a main software product that matches fleet drivers with users looking for cabs.
Cool. Wait, we'll come back to this in just 1 second. Chris, I have a question for you. Choose one of these and answer it about the guest lecture. I know it was 7 days ago, which feels like forever ago, but
I thought his strategy was really cool, talking about how he was trying to go into all these different spaces and then how he acquired them.
I agree. Yeah, I think he mentioned he acquired someone named Rick's company.
Yeah.
Rick was supposed to give the lecture, but he's traveling. But yeah, it's pretty cool that it's big enough to acquire other things. So Awesome. Thank you for sharing that. Okay. Yes, Madhav, can you repeat what you just said?
Yeah, so Uber is a technology company that mainly has like one software product whose purpose is to like match fleet drivers with people looking for cabs.
Cool. Okay. Can someone else explain to me, like, if I were to use the Uber app, what exactly do I do, and like what goes on? Like, what's the user workflow? Alex?
Specify where I want to be picked up, where I want to go, and what type of car I want.
Okay. And then what happens? You like click some buttons?
Yeah, you click some buttons and then they find a driver who picks you up and then sends you to your place.
Right, yeah. So like there's that little in-between time where they like find your driver and it's like, okay, Roberto will pick you up in like 10 minutes. I ran into that issue this evening. It was super annoying. Does anyone know how that matching occurs? Like, how does it figure out which driver should pick me up?
I guess like just from experience, like all of the drivers like in your neighborhood who could like reasonably be there, I'm guessing like 10 minutes or something, get like a prompt on their end where they can like choose to accept the ride or not, and they can see exactly like how much they're going to make from the ride and like what the estimated ETA is. So it's like sort of on the driver to decide like if they want to accept it or not.
Okay. Yeah. Good. Okay. Nisha.
I guess at a more like grassroots level, figuring out like in what order to show that prompt to drivers, because of course at any given time it's only shown to one person and they have like a very short, like I think like 10 seconds or something to click on it. I feel like it's some sort of like very quick shortest path algorithm to like try and get to you. But I think there's also like for Uber specifically, just because of how many times we all use it, there's a lot of things that go into that decision. Like I think if you're a really highly like rated user, then they try and match you with like highly rated drivers and stuff like that. So it's not like a simple algorithm with like one input, one output.
Like, I don't think it goes to only one driver at one point. I think it like flashes for a lot of people and whoever like clicks it first sort of gets it.
The way I've seen is that like that bar sort of progresses and it's only on one person's screen for like 10 seconds.
I think a lot of
be surprised.
You know, I don't think it really matters. But like, I guess the point is that like there are many different ways that a driver could be, you know, assigned to you. For example, like if I wanted to take an Uber to like, I don't know, what's it called, Pattaya or something. It's not going to give me an Uber driver who's currently in like Des Moines, Iowa, right? It's obviously going to be something somewhat nearby. Hopefully, by the end of this class, we'll be able to solve a problem very similar to what Uber does. So let's just keep this as inspiration as we go throughout lecture. Okay. Now, we'll just ground ourselves before getting into the stuff. So past few weeks, we talked about LP, linear programming. We had this linear mathematical function that we wanted to minimize or maximize, and we had linear constraints. Then we had integer linear programming, which was the same thing. Linear function, maximize or minimize it, linear constraints, with the extra constraint that all of our variables must be integers. And then we said that there was mixed integer programming, which was kind of like the same thing. Linear function, maximize or minimize it, subject to linear constraints. Now some of our variables can be integers. But our world isn't only linear equations. Like we spent some time exploring some other equations, but like we never really changed our constraints very often. There are many, many problems out there where the constraints on a problem aren't these functions of variables that happen to be linear. They can be a lot more abstract. So today we'll like step outside of this mixed integer programming world to something a little bit more general, but it still encapsulates mixed integer programming, but it can handle some more complex constraints. That's why today's lecture is constraint programming, because that's what we'll be talking about. So we've used the word constraint a lot throughout the past few weeks, and it's about time we give it a definition. However, that definition seems to match like the English understanding of what the word constraint is, so this shouldn't be too surprising. But like, okay, before we get into that, many of the problems that we deal with involve like finding a solution to something and ensuring that that solution abides by the constraints. For example, in the spirit of Uber, maybe a problem is match me with an Uber driver who will pick me up within the next 20 minutes. Well, obviously, it's not going to give me someone in Des Moines, Iowa, because that is an Uber driver, but the constraint is getting to me in 20 minutes, which they can't. So instead, a more correct solution would be someone like right down the street who can get to me in 20 seconds or 20 minutes. So again, find a solution, but it has to match these constraints. And a constraint is simply just a rule that limits like which possible solutions are acceptable. For example, the rule is get to me in 20 minutes. And we've talked about SAT a lot. So in the spirit of SAT, the solution that we look for is a truth assignment. Truth or false to each variable. The constraint is that each clause needs to have at least one variable or one literal in it that evaluates to true, so as to satisfy the entire formula. Still should be kind of in our comfort zone because it's pretty much all we've been doing the entire semester. Questions thus far? Okay, so then a constraint satisfaction problem, which is what we'll be dealing with, it's officially defined by two things, or like you have to have two things to describe a problem. First is a set of variables, each with its own range of values. That just means each variable has a defined set of things that it can take on, and a set of constraints. So let's just see an example. So in the world of 3-SAT, maybe our formula looks like this. Let's just change it to this. And we can say that the SAT problem is a constraint satisfaction problem because we indeed have variables being x1, x2, x3, x4. They need to have a range of values. So what would the values for one or all of the variables be in this case? Like what could they potentially take on?
Either true or false.
Yeah, like the values for all of them come from true or false. And then, of course, the constraint is that like one thing within each clause has to evaluate to true for the formula to exist.
It's sort of explaining why integer programming can't be linear, even though it's linear programming. Sorry, it can't be done in polynomial time, even though linear programming is. Because if you can do integer programming in polynomial time, you can do SAT in polynomial time.
Yeah. Yeah, there's a pretty simple reduction there. Good. Okay, so then just for some extra vocabulary, a candidate solution is any assignment of variables to values. So I'll give a couple of candidate assignments. So both of these are candidate solutions because I am giving values to my variables. And we call a candidate solution feasible if it satisfies the constraints. So this first one is not feasible because just substituting into the first clause, none of them evaluates to true. But the second one is feasible. Or in the Uber example, the Uber driver in Des Moines is not feasible, but it is a candidate solution because they are a driver, but the Uber driver down the street is feasible because they can get to me in 20 minutes. Make sense? Okay. So we saw a solver for integer programming or mixed integer programming. It was that like OR tools, and you might remember glop, the linear programmer, things like that. So whatever. OR tools happens to have something called CPSAT, which is going to be a tool to solve constraint programming questions. And we haven't really like you can imagine SAT as an instance of constraint programming. We'll see other examples of problems that are constraint programming that'll be a bit more tangible. But yeah, we can use this library to solve those problems, and we'll talk about it soon. And as a very gross oversimplification of what goes on, it takes the constraints and turns them into clauses and solves an instance of SAT. That's why it's called CP-SAT, but there's a lot more that goes on behind the scenes, and honestly, I don't really know all the details of that. But it's very successful. It can solve a lot of really great problems, and that is what we're going to choose to use. So yeah, today we'll talk a bit about like programming with CP-SAT, while along the way solving a few different problems that are like kind of interesting. So in case you want to look at the documentation, you can refer to this slide.
OR tools is created by Google.
I think so. Maybe originally it was not, and then it was acquired by Google, but I think it's Google's in-house thing. Yeah. There's a lot of different functions that can be done with your CP solver, but documentation is there. Okay, so like first we'll talk about variables, and I'll try to contrast them with what it was with the mixed integer programming solver. So, you can define different types of variables, except here we're a bit more constrained. In fact, CP-SAT only allows for these integer variables and Boolean variables. And this was the same thing in our mixed integer programming. We had integer variables and we had Boolean variables. We also had something called numvars, which were allowed to take on decimal points, but that's not allowed in CP-SAT. You might ask why? The answer to that is I don't really know. I tried researching it and they were just I don't know. So if you find out the answer to that, great. But we'll see some hacks of how to allow for decimal values. Yeah, just as we did with the mixed integer programming solver, you'll specify a lower bound that variable can take on, as well as an upper bound, and then give it a name. And we'll program with it in just a little bit. And yeah, this last point here is the most important, that CP-SAT only works over discrete finite domains. So the numvars from before aren't going to happen. They're going to be integer variables. And we can't have infinite bounds. We have to specify some sort of upper bound, some sort of lower bound. Hopefully, you kind of remember some stuff from the mixed integer programming solver. I know it was a little while ago, but maybe you're seeing some similarities. Okay, and then still continuing from the world of mixed integer programming. Remember, in that diagram that I showed where we took the step back into that yellow circle and there was the question mark, within it was still mixed integer programming. So we want our CP constraint programming solver to still handle mixed integer programming instances. So, if you want to specify linear constraints, you can do that. So linear constraints were x1 plus x2 can't exceed 5. Or maybe 2x1 minus x3 has to be at least 2. Those were examples of linear constraints. You can still do that. It'll look pretty much identical to mixed integer programming. However, the whole point of constraint programming is to allow for more complex constraints, things that aren't just things that look like this, because that would get really boring. So you can also add not equals if you desire. There are a lot more constraints that we'll talk about in just a couple minutes. Question?
By definition, if you have not equals, then you can also have strictly greater than and strictly less than. Right?
Yeah, but I think our definition of linear inequalities said that the inequality symbol had to look like that.
Sure, but
so unless you do some sort of scale down by or add one, subtract
you
one.
just for example, if you want to add 2x1 minus x3 is greater than 2.
Yeah.
And they just add that constraint 2x1 minus x3 is greater than equal to 2, and then also 2x1 minus x3 not equal to 2.
Do you have add?
Well, add them as different constraints.
Oh,
Well, yeah, that would, like, if you add 2x minus x3 is not equal to 2.
So is greater than equal to 2, and you add 2x minus x3 is not equal to 2. You add
Not
both of
equal
them.
to 2.
And yeah, at the top, out there, greater than equal to.
Yeah, okay.
If you add both of them, isn't that just effectively adding the greater than?
Yes, that does do greater than. But we couldn't do this in mixed integer programming.
No, but now you can.
Now you can. Yeah, now you can do not equal to. Yeah. I think you can probably just use greater than 2 here. I'm not too sure. And yeah, like this whole thing about fractional values, it's important to note, like, our coefficients must be integers now. We can't be dealing with decimal points all the time. And so I mentioned that there's like hacks you can do to get around it. So here's a potential hack. You know, suppose we wanted to solve this mixed integer program, which we know how to do using our other tools. But suppose, just for the sake of fun, that we wanted to solve this using our CPSAT solver. So the true solution to this mixed integer program is x1 equals 3.8, x2 equals 1.2. If we fed this like problem into CPSAT, it would not return this. Because in order to define this, we have to define our variables, x1 and x2, and CPSAT only allows us to define them as int variables. So it would return to us integers. So whatever CPSAT gives us wouldn't be the correct solution to this. However, we can slightly hack our problem to give us the correct answer. That is, we can get integer values that are equivalent to this by scaling our constants here by a factor of 10. And really all that does is scales our variables, their correct values, but, oh no, did I not include the answer? Ah, darn. Okay, so this would return like x1 equal to 32 and x2 equal to whatever it was, 18? So we've scaled it by 10, we would get these integer outputs, and then manually we would scale them back by a factor of 10. So the point of this is like, we can solve these mixed integer programming things using CPSAT. You can get around the decimal things with some hacks of scaling values. That's the main point. You can get them by scaling things, but at the end of the day, just solve this using a mixed integer programming solver.
Isn't this a bit like paradoxical? Because like sure, like in this case it was like it worked out perfectly, but like the CPSAT, like linear programming, for example, even if you have like a number that's not, even if it's not rational, it'll still like output it, right? Like for example, if like hypothetically pi was your correct outcome, it'll still output it, and no factor of scaling will get you even close. So like the same reason with why like for integers, it's possible that the integer solution is very far from the mixed integer solution. It's possible that like even if you scale it by like 10,000, you get an answer very far from like you don't get 31415, you get like something very different. Yeah, like the computer solvers are going to round at some point because they can only output a number with so many significant figures. But yeah, like this thing about like, oh, we scaled it by 10 and it works out nicely. We scaled it by 10 because we knew there was only one decimal point in the answer, right? So you would have to guess your scale, I guess. But like, if you wanted to solve this, just use the mixed integer programming solver. But the point is, there's a hack, but I don't think it's too important. Good question. Other questions? Okay. I'm sorry, I'm going to be pausing a lot today because it's been a pretty bad week and I finished this lecture in the Uber ride here. So I'm still trying to figure out what I'm supposed to talk about. Okay, I did that. Okay, let's talk about some better constraints. These might not immediately make sense why you would want them or like where they would be applicable. Yes, it might not make sense where they would be applied, but hopefully you figure out that, hey, this could be nice to have at my disposal. So again, we're moving away from those linear constraints altogether. Things that look like this, we can still handle, but now we're going to be able to handle a lot more constraints. So this first one is add multiplication equality. And you specify two parameters, a target and then an array of variables. And this will give us the constraint that whatever target we specify here,
needs to be equal to the product of variables. So, you might want a constraint that looks like x2 equals 3x3 x4. Where this would be a constraint for what problem, who cares? But maybe we want something like that. Just maybe we would want something like this. And it's as simple as defining it like that. Also, add max equality, which sets something equal to the maximum of an array. So maybe we want x3 equal to the maximum value of x1, x2, and 100. Again, who knows when we'll use it, but that seems like it's pretty helpful to have. And so I know this seems kind of boring, that it's just I just have to type that and I get a constraint. But really think about what we're doing here. We spent so much time just solving problems with things that look like this, and now we're taking a huge step to account for a lot more constraints, which happens to be done very, very simply syntactically. So, kind of appreciate it. Here's another one, the all different constraint. Maybe you have a set of variables and you want to ensure that all of them take on a different value. That's very easily done just like this. And we'll actually see this one in action. Okay, I won't talk too much about that. Okay, so we'll see our first example of a problem right here. And this is called cryptarithmetic. I don't bloody know. I'm going to call it cryptarithms for now. The idea is that you're presented with some sort of mathematical equation using letters, and you want to figure out what value should each letter be so as to evaluate the expression and everything matches. So as an example, on the left-hand side, you see an instance of the problem. On the right-hand side, you see a correct mathematical equation, and there's a one-to-one correlation between the letter and the value. So A must be equal to 9, B must be equal to 1, and then B matches here, C happens to be 0. Do people understand how this works? Any questions on this? Are you sure? Okay, well then if that's the case, do not flip these over, but get out a pen or pencil. Don't flip it over. Get out a pen or pencil. Don't flip it over. Get out a pen or pencil. Don't flip it over.
For everyone?
Yeah, for everyone. But the proposal is still due on Monday.
Yeah.
At least for now. Okay, so in front of you, when you flip it over, you're going to see a different instance of a Cryptarithm problem. Your job is to solve it. Whoever solves it first, $5. Go. Correct. All right, we have our winner. I don't know what you can get with $5 in this economy, but I'm not willing to give too much more money. Okay, the answer is this. Yeah, so since Chris, you want to explain your thought process instead of me?
So I knew n had to be 1, and then I tried with s equals 9. So I knew that s had equal 9 because O couldn't also be 1, so that had to be 10. And then I filled in the other O, and then I noticed that E and N are different in the hundreds column. And if O is 0, then there has to be a 1 carried over from the tens column. And then N has to be 1 more than E. So then I just tried every pair of one-away numbers after that. And 2 and 3 didn't work, 3 and 4 didn't work, 4 and 5 didn't work, and then 5 and 6.
Nice. Awesome. Yeah, good job. Cool. So, this problem's not going to pop up everywhere you go. You're not going to walk down the street and someone's going to give you a cryptarithm and say, I'll give you $10 if you can solve this. But it's like a fun little puzzle, and it's a good introduction to constraint programming solvers. So we're going to solve this using our CPSAT solver. And in order to do that, we'll just formalize a couple of things, and then we'll code it up, and you'll just see an introduction to how the CPSAT solver works. So we'll use this instance of the problem that we're going to solve. So for our constraint programming, we need to define our variables, and then the values, and then the constraints. So the first two should be hopefully easy to describe. So variables, what are they in this example? Like what things are taking on different values or could potentially take on different values?
S-E-N-D-M-R.
Yeah, the letters. So S-E-N-D-M-O-R-Y. And then the values.
0, 9.
Yeah, so the variables will take on values between 0 through 9. We don't know what they are yet. That's what they're, that's their range of possible values. And I guess we know from this problem that there aren't any leading zeros. I probably should have mentioned that at the start, but we brought that up. So in particular, this range holds for most of the values, except M and S, which will have 1 through 9, because it's non-zero. And we can make further observations that M has to be equal to 1, but let's just leave it at that for now. Okay, so that's that. What are the constraints that we have to abide to in solving this problem? And part of it just comes from the definition of the problem. Well,
all the variables must be distinct, like their assignments must be distinct.
yep. Variable values are distinct. What other constraints do we have? Arish?
Like the constraint of actual addition.
Yeah. The arithmetic has to hold. Okay. That is describing the problem. Try solving this using linear programming. You're not going to be able to do it, right? These constraints are much more complex than those x1 plus x2 is less than or equal to 5. But good. This is describing the problem in the world of constraint programming. Let us solve it. So, oops, that's a little too big. Okay. Visible for the most part? Yeah. Okay. So at the top, we're importing the CP model from OR tools. It's from the SAT library because of how it's solved. And Python, we're importing CP model. And then we're just instantiating the model itself in this second line here. And then we go about doing the same thing as we did with mixed integer programming. Essentially, just define your variables, define your constraints, and solve. So we'll define our variables, S, E, and M, O, R, Y. So I'll show S, which is equal to, okay, yeah, I have Copilot on. You guys shouldn't have Copilot on when you do your homeworks. Let's just say, okay, we'll say 1 through 9, because we said, S is that range. And the third parameter here is just giving it a name. So we're calling it S. And then we do the next thing for E. And I only have this on for the sake of lecture to not make it super boring and long. But you guys should not be using Copilot. Agree? All of the variables defined. We've specified their lower bound and upper bound, which is the values. That's that. Now we specify our constraints. Let me turn it off. Okay. So the first constraint we said is that the variables are all different. This seems like it's potentially a difficult constraint to add, but we actually just talked about this on a previous slide, and it's just like model.add all different, and then we would give it an array of the variables. So let me just create a variable array here.
Otherwise, you could add like pairwise not equal to, right?
You could, but that would be annoying, right? One line.
Not with the autocomplete.
Yeah, nor with like ChatGPT. But yes, okay. Boom, first constraint done. Second constraint, the arithmetic has to hold. How do we do that?
You can say something like S times 10,000 plus E times 1,000 plus N times 100. Like basically get into like their actual values.
Yep. Yeah, we're just gonna like write it out. So like construct the word send. S is in the thousands place, so we'll multiply it by 1,000. Oh, this is gonna be so annoying to type out. So that's send, and then more is 1,000 times M plus 100 times O plus 10 times R plus E. And this has to be equal to 10,000 times M plus 1,000 times O plus 100 times N plus 10 times E plus Y. It looks pretty similar to like what we did with mixed integer programming, adding constraints, where we do .add and then we shove in the equation. Same idea here, just looks a little bit more complex. And then we can run the solver, and a lot of this is just syntax to make the output look good, but it's pretty similar to what we did before, where we check if it's optimal and then print it out if that's the case. So if we run this, well, you already saw the output, but it gives us the answer. That's the answer from before. So it's a pretty simple example. We might see another more complex example in just a moment. But yeah, that's the introduction to our CP solver tool. Questions on any of that? Cool. I hope that it's recording. Yeah, it should be. Okay. In the problem that we just did, we weren't really optimizing anything. Like there was no objective function that we were maximizing or minimizing. We just said assign our variables values subject to these constraints. However, if you wanted to optimize something, maximize or minimize, you can do it the same way as we did with the other solver.
What would it have done if it had multiple solutions?
I think like it would have stored all of those solutions and you could have printed them all out. I think here it just checked if one of the solutions it found happened to match the optimal. In that case, it outputted it. Yeah, good question. Okay. Couple more constraints that we'll talk about. So add element. This will, you specify an index, you specify an array, and you specify a target. This will add the constraint that the target has to be equal to some some element of our array by the index. And that might seem pretty boring. Like, why would you just say that I want, the third element of my array when you could just specify that? The nice thing is that this index doesn't need to be a constant. It could be a different variable. So you could select a different element of your array depending on what your index is. So that's that. Again, might not make sense why we would use it, but it's a nice to have. And this one's super, super complex. Yeah, I don't even know if I can explain this correctly. But there's this thing called add inverse. and you specify two arrays, both of size n, and the values within the arrays, let's see, it's called var array and int array or something. Oh, inv array, okay. So the values within them are going to be like 0 through n minus 1. And when we add this constraint, it will rearrange the values within our arrays such that this nonsense holds. And what is this nonsense? You can kind of think of it as a matching in a way. So if I have if I wanted to construct what the output would look like, suppose the number 2 ended up here. The add inverse array, let me just say index 0, 1, 2, 3. So let's say that we put the constraint in, it outputs an array, and there happens to be a 2 in the var array. Then, if this constraint holds, then the value of 1 must be placed at index 2 of this array.
Isn't this just a for loop? Can't you just iterate over the first list and populate it that way?
You could, yes. But this is saying we have two arrays, maybe there are variables in our problem, and we want this relationship to hold as we solve different things. So maybe we see in V, index 2 has the element 0. The constraint tells us that in this array, index 0 must have the value 2. And this would be can you even do this? 1, 3.
Ishan, I'm still fully not sure what's happening here. Is our second array also something that's given to us, or is it being created?
When you use this, you will probably specify an array, and you want a relationship between two arrays. We'll see a problem in the next slides where we will use this, and hopefully then it'll be a little bit more clear. Because when I was trying to figure this out, I was like, this is super hard to conceptualize, but in context of a problem, it might make a little bit more sense.
Can we just go back one slide?
Yep.
When we're saying sort of a similar question, but I'm not sure which array it's using as the base.
Yeah.
Does it set the value for the other, or does it not need a base?
I wouldn't even think of. Okay. Sorry about that. Just lots of things going on. Okay. I understand this constraint is kind of confusing. We'll see it in an instance of a problem. Let's say right now. So think about the Uber inspiration from the start of class. This is going to be a problem that is kind of similar to what Uber may do. So yeah, here is the description of the problem. There are n customers, maybe n Uber users, who are all waiting to be picked up by their Uber driver. So you can imagine n people, maybe all of us in this room, and we all request an Uber at the same time. And there also happens to be exactly n taxis available to us. We know the distance between each taxi and each customer. So maybe the idea of all of us being customers in the same room is a pretty bad example, but you can imagine scattered customers. We know the distance between each car and each person, and the distance that they have to drive to pick them up. Our goal is to assign taxis or Ubers to customers in order to minimize the total distance traveled by all of the taxis. That's the problem. Seems like something Uber might want to solve. Do we have questions about the structure of the problem? Because that's critical in solving it. Okay. Then I'll call this the Uber problem. Yeah, our input and output is there. Okay, let's just Yeah. So a visualization of what's going on here. We have n people, 4 or more, n taxis, and we know the distance between each person and each taxi. So as an example, for a single person, we know that the first taxi is 12 kilometers away from them, the second one is 8 kilometers away from them, so on and so forth. And each person has, their own distances. And our goal is to assign a singular taxi to a singular user so as to minimize the total distance. So any other assignment, for example, would yield further distance traveled by the taxis. Okay, pretend this was like an algorithms class. Maybe you're sitting in 121 or 320. And what seems to be the most naive approach that might seem like it could work, but actually doesn't?
Just try all possible routes, sum them up, and then sort that list.
Okay, but if n is very large,
Yeah.
that'll take a really, really long time.
Yeah, route first.
What other solution? Well, what's an intuitive, greedy idea?
Take the first person, give it the first taxi or the first person, and take the first person assigned the taxi the shortest distance, remove the two of them, and keep going.
Yeah.
Yeah, that probably doesn't work.
Let's just say, let's find the least weight, and by weight I mean shortest distance, unmatched person taxi pair. So at the start, no one has an assignment, but maybe taxi 3 is half a kilometer away from person 2, and that's the shortest distance, so we'll assign that to them. And then we look at whatever's remaining, and then, go from there and choose the least distance there. So this, maybe not obviously, but unfortunately it doesn't work. And just to give a proof or a quick counterexample, imagine we have 2 people. Let's say there's a taxi here. Let's say it's 2 kilometers from person 1. I'll call this A. And 1 kilometer from person 2. And maybe there's a second taxi here, which is 2 kilometers from person 2 and 5 kilometers from person 1. So then with our naive attempt 1, we would say that this pair is, the shortest distance. So we would say 2A is a pair, and then we would have to pair 1 with B. The total distance traveled by the taxis is 1 plus 5, so this yields 6. Whereas if we match 2 with B and 1 with A, it gives us 4. Okay, so the naive attempt doesn't work. Question?
Doesn't it seem very simple with the CB solver? Just throw in all these pairs 2A, 1B, whatever, and against the distance, and then just put constraints that everything needs to be there once.
Yeah, I mean, if n is small, if we have 4 people, sure, go for it. But if n is very large, then what do you do?
Would there only be n square pairs?
Yeah.
Yeah, so that's not that bad.
Well, if you have 100 people, are you going to specify all 10,000 constraints? Maybe not. Okay, so attempt 1 doesn't work. So we'll turn to attempt 2. So with everything in life, when the greedy solution doesn't work, what do we turn to next? Constraint programming, obviously. So we'll solve with constraint programming. Okay, so we're going to define our variables and then define our constraints. And so this is where things get a little bit strange. The way I define my variables may not be entirely intuitive. You might think okay, maybe we want a variable for each person, and each taxi. That is kind of true. However, we're just going to go with this definition that I supply and just live with it. So we will define arrays called passenger of and taxi of, such that when I index the passenger of taxi J, when I get my assignments to my arrays, this will return to me some passenger, which we'll call passenger I. So this first array will tell us who is riding in a taxi if we have the taxi number. So in this case, at index, let's say that's 0, 1, 2, 3. At index 0, we would have the person number 4. At index 1, we would have person 1. At index 2, we would have 0. Wait, what? No, this should be 3. And then at index 3, we would have passenger 2. And similarly, we'll have something called taxi of, which kind of goes the other way around, where taxi of passenger I will give us taxi J. So wait, in the example, what was this one? 3, 1, 0, 2. So the taxi of array, taxi of person 0 is 2, 2, 1, 0, 3. Kind of clear? Make sense? Okay. So our variables aren't necessarily the arrays, it's more or less the values within the arrays. And we can think that let's just let x be an element of one of the arrays. We can imagine that x would have a lower bound of 0 because the smallest passenger we have is 0, and an upper bound of n minus 1. Smallest passenger taxi we have is 0, largest passenger taxi we have is n minus 1. So we would define variables within here, each one with this lower and upper bound. However, when we turn to constraints, constraint 1, perhaps the most important constraint that is more or less a given is that if passenger I is matched with taxi J, then we also have to have taxi J matched with passenger I. That's just the definition of a matching, right? Like one way and the other way. However, this happens to be exactly what that obscure add inverse constraint was all about. In particular, if we look at a passenger of array, let me write it out properly. That's not properly, that's ugly, but deal with it. Yeah.
It should be 2130, right? The taxi of
2, 1, 3. Yeah. Thank you. Good catch. So, in particular, if I have, say, the value 2 here, saying the passenger of taxi 1, because we're looking at index 1, is person 2, then the taxi of person 2 should be taxi 1. There's this relationship like that. And similarly for everything else. If the passenger of taxi 0 is person 1, then the taxi of person 1 should be taxi 0. There's that matching relationship. So the way we encode this is with the model dot add inverse of the two arrays.
And this is like always true no matter like what the assignment is, as long as it's like 1, 1 and 1, 2.
Yeah, no matter what the assignment is, even if it gives us the worst distance,
Yeah.
we have to have this
Yeah.
relationship. That's what add inverse does. Are there any other constraints? No. Okay, good. And then the goal of this problem is to minimize the distance traveled. And so here you can basically just like, you can just figure out like the matchings and then add it all together. Let's just code it up really quickly, because that might be a little bit more
Usually
interesting.
find like those pairs and then add the distance.
Okay, so some more variables that exist. So not just constraints, but variables. CPSAT defines something called interval variables, where it's defined by a start time, an end time, and a duration. So maybe you're like assigning jobs to different people, and they all have their own timelines. And the job needs to have a start time, and it has its duration, and it also has an accompanying end time. And, maybe you're assigning those jobs. And in that case, you would want to use interval variables. And it'll enforce the thing that like the end time must be like duration amount after the start time. But this is a pretty cool thing to have, and it might be used for job scheduling problems. And there's also, not a constraint, but a specification to add no overlap. So if you're assigning these jobs to people, maybe they can't do many jobs at once. So if you say no overlap, our solver will just make sure that there is no overlap. And in fact, the problem that like we'll briefly look at is this jobs shop scheduling problem. I need to drink some water because I'm losing my voice. So this problem is described. You have M machines that do tasks, and the tasks are described to you. Okay, we'll talk about that in just a minute. Machines can only do one task at a time. They cannot multitask. And once they start a task, it has to be completed before they start something else. You're also given jobs, which are different from tasks. A job consists of tasks, and each task says, hey, I must be performed on machine 2, or hey, I must be performed on machine 3, and I take some amount of time to complete, 4 minutes, 5 minutes. So a job has these tasks, and the tasks have to be completed in order. And our goal is to minimize the make span, so the time to finish all jobs. So, here's an example right here. We have 3 jobs. The first job has 3 tasks, and it says my first task, which has to be completed before the second 2 tasks, this task has to be performed on machine 0, and it takes 3 units of time to complete. And once that's completed, then I can do my second task, which has to occur on machine 1 and takes 2 units of time to complete. So all 3 jobs must be complete, and within them, the tasks have to be done in order. So here is a potential solution. So let's focus on maybe job 1 for a moment. And we see at the start time, machine 0 is given the first task of job 1. And that happens to take 2 units of time. So looking here, that checks out right there. The next thing that has to be completed is on machine 1, it takes 1 unit of time. And we see that does get taken into account right there. Sorry, I can't read, that says 2. And then lastly, this task, machine 1, 4 units of time, that does get done after the first 2 are complete. It's a very complex problem, but hopefully it kind of makes sense. And so Let me just show you the solution, and then you can look at things on your own time if you want. So the make span it gives is 11. These are the assignments. It improved it by 1. Which, I mean,
Yeah, for
not
me, it's
terrible
fine.
given 3 machines and 3 jobs.
Almost 10%. So.
Yeah. So more jobs, more machines, maybe better improvement. Okay, that's it. Homework's due on Tuesday now. Do you want the project proposal also due on Tuesday?
Sure.
Yeah, okay, that's due on Tuesday as well.
Wait, project proposal or the groups?
Proposal. Groups are due tonight. Take care, good luck tomorrow.